Now that I have all of this information about my function f of x that I've got from f prime, f double prime, I'd like to be able to at least understand what the graphs look like. And I have this amazing piece of technology. I just have one problem. If I graph this first graph, there's my picture. That's f of x. Let's turn off f of x and graph g of x. That's the graph of g of x. What the fuck? What's wrong here? I've graphed both of these functions, and all I see is an empty screen. It's on there. It's got points. It's graphing this function. But what's going on here? That's the graph of f of x. It's drawn it. If I hit the trace button, it's got points. What's the problem here? The window. The problem is I don't know what this graph is supposed to look like. I don't know where to look. Even if I look at this trig function, it's a sine curve. It shouldn't ever be bigger than 2, smaller than -2. I'm even going to go in and change my window, so I only have to look at those. When I do that, is that a useful picture? Okay, I'll change my window. -6 to 6. That's perfect. That's also wrong. That is 100% a lie. It's just that the computer is stupid. All it does is plug in the numbers. This curve should be wiggling back and forth like there's no tomorrow. But the way I pick the window changes the picture I'm going to get. That makes sense. So how do I know what to do here to get myself a good picture? By the way, the strategies I'm about to discuss existed well before graphing devices. These ideas actually work for drawing these graphs by hand. But I have a computer that's going to do this. I'm going to use it. I just need to know where to look. Because otherwise, I know that graph is supposed to be a parabola. Where's my parabola? I'm just looking in the wrong place. So I need a systematic, deliberate, algorithmic, methodological way to trace out the steps I need to know where I should make my window to draw this picture. I can learn information from f prime, from f double prime. If I can get information from each of these, what information can I get? So let's think about the original function f. Ignore my derivatives for a moment. Let's just think algebra. If I want to know where to look to see a function, what's the first thing I should start with? Thinking about my function.
Where do you put zero?
Yes, the intercepts would be good because then I could have plot some points, right? And if I can plot some points, I'll be better off. Okay. Where it's equal to 0, those are the x-intercepts. I can also get the y-intercept by plugging in x equals 0. Maybe. When might this be a problem? I don't know if I'm allowed to plug in 0 to my function. What if I do 1 over x? I can't plug in 0, right? So maybe before I even try and figure out where things cross axes, I should see if I'm allowed. Let's look at the domain. Because that tells me where the function lives, what x values are allowed in. If I did the square root of x, it doesn't make any sense to look where x is negative. If I do tangent of x, I know I'm going to have a bunch of vertical asymptotes. So I've got options there. But yes, finding the intercepts will absolutely help me out. Going further, I can look at things. Hey, I was looking at a trig function before, right? Sine of 50x. That repeats. So if I know one period, I know the whole thing. You were asked to graph a function for me, knowing things about its derivative way back in chapter 2. I said, suppose we know that the derivative is 1 here and it's 0 here. Sketch me a picture. One of the homework questions asked you to use the idea about the function being even. So I can think about the symmetry. Now, maybe we don't have any symmetry. Maybe we don't have any period. Maybe we're not dealing with a function that looks like that, but I should at least check. I should check for asymptotes. Vertical asymptotes are related to my domain, but horizontal asymptotes are related to going out to infinity. So I might need L'Hopital's rule there. That's plenty of information just from F alone. Before I draw a thing, where should I look? Where do I cross axes? Can I get away with looking at a smaller section? Can I look at one side and then deduce something about the other? Do I know anything about any asymptotic behavior? I like that. But this is calculus. All of this is algebra. Haven't done very much calculus here yet at all. But if I take a derivative, what's derivative give me? What's f prime tell me about f? This was Friday. I didn't dream Friday, did I? You all were here. I didn't hallucinate you into being. Okay, good. What does F prime tell me about F? So it's the derivatives information tells me how F behaves. But what characteristics of F? Chase?
We get extremes.
Where we're going up, where we're going down, we get the highs and the lows. Highs and lows are going to help me figure out parts of the prop window, right? Okay, wait a minute. So I get maximums and minimums. Hey, wait a minute. That piece right there, that should give me most of the information that I need for my window. But we learned more about my function, not just from F prime, we learned about F from F double prime as well. What did F double prime tell me about F? Convexity, where it was curving in different behavior, right? Now, we talked about the concave side rather than the convex side. And I have my little mnemonics here to help me remember what's going what. And where we change convexity, those are our points of inflection. I can also use the second derivative to help me find the maximums and minimums by using the second derivative test rather than the first derivative test. So I can put all of these sorts of things together. And I can figure out what's going on with a function before I graph anything. Then I can draw a good picture. Now, I will admit, I was taught to do this with nothing more than a sheet of graph paper and a ruler. But everything I'm doing applies regardless of the level of technology you have. So here's an example. I'd like a decent graph of this. I want to do this process. I want to run through all of these steps and use them to help me get a picture that encompasses all of the interesting bits of this graph. And I want to be able to label those. So let's start over here. Can I figure out where this is equal to 0? Oh, wait a second. Let me do the domain first. I think that might be helpful doing that one first. What kind of a function is this? And that list of categories back in chapter 2 about functions that in their continuity and their derivatives, we had this big list. What kind of a function is this? Big list kind of functions, chapter 2, section 5. What kind of function am I looking at? Okay, and we know polynomials are defined and continuous where? Everywhere. So the domain of this function is all real numbers. It's defined everywhere. And that means I could plug in any number I want, including plugging in 0. So when I go to find the x-intercepts, or the y-intercept, sorry, I go to find the y-intercept, f of 0 is 0. That means that 0, 0 is a point on this graph. What's more, that makes it not just the y-intercept, it also makes it one of the x-intercepts. Can we solve that equation? Okay, let me phrase it the other way. We can solve this equation. I would like you to do so. The result is not pretty numbers. If I factor out an x squared, 8 minus x squared equals 0. Well, if x squared is 0, then x is 0. If this piece is 0, I get 8 is equal to x squared, which gives me plus or minus the square root of 8 for my x values. And that's not a pretty number. But the square root of 8 is somewhere between 2 and 3. Probably pretty close to 3 because square root of 9 is 3. So this is like 2.8 something. I'll leave it as the square root of 8, but I remember this is between 2 and 3. Okay, that's intercepts, domain, symmetry. This is not a trig function. I don't have a period, but is this function symmetric? Why? Unfortunately, it isn't. Parabolas are only quadratic equations, x squared. There's an x to the fourth here as the highest power, so it isn't truly a parabola. But let me go back to the definitions for my symmetry. A function is odd if it's got that diagonal symmetry, right? What's up on the right is down on the left. What's up on the right is down on the left. If I change the x to a negative x, I go from being up to being down. And it's even if f of x is the same as f of negative x. So it's the same on the left as it is on the right. Notice that both of these require me to put a minus x in. So let's do that to this function. F of x is 8x squared minus x to the fourth. What's f of minus x? Well, 8 times minus x squared minus minus x to the fourth. What happens when you square a negative? That means this is the same as 8x squared. X to the fourth, I take a fourth power of a negative, that's squaring and squaring again, right? So it's going to become positive. Wait a minute, that's the same as the original. And that means the graph of this function is exactly the same on the left side as it is on the right side. So now I know if I just work out values over here on the right side, I'll get the negative ones to be the same. I also know this is a polynomial. Polynomials don't have asymptotes. There are no vertical asymptotes because it's defined everywhere. And there are no horizontal asymptotes because both ends, fourth power, go up or down, depending on whether the coefficient is positive or negative. They go the same direction. It's a negative, so they both go down. That means this graph is going to come up on the left. It's going to go down on the right. There'll be a bunch of wiggles in the middle. Right now, if I were to make any sort of graph, I would know three things. I have a point here at 0, 0. I have a point here where x is the square root of 8. And I have a point here where x is negative square root of 8. That's all I've learned so far. But that's just for math. Let's do some calculus. What's f prime? And since I'm going to need it later anyway, I could work out f double prime right now too. Great. You can deal with these one at a time. You can deal with them together. It's up to you. In order for me to learn stuff from f prime, I need the critical numbers. Critical numbers are where what is true. Or there are the endpoints are only when I've got an interval given to me. I don't have an interval in this case, so I don't have to worry about endpoints. But there are two conditions for critical numbers. One of them is where it's 0. That's what the critical numbers are going to tell me. The other option for a critical number is that my derivative is undefined there. But this is a polynomial. It's defined everywhere. So critical numbers is where f prime is 0 or f prime does not exist. Polynomial. This is out. I don't have to worry about that part. Polynomials are good everywhere. So I don't have to worry about where f prime is 0. Where does that happen? Back to my algebra. I need to factor this. Solve it, set it equal to 0. Understand what those values are. What do I do, Dean? So if I take out a 4x, I'm left here with a 4 and here with, okay, that's 0. Now what?
Then you go x equals plus or minus 2.
Aha. And that makes sense because what's happening on the right should be the same as what's happening on the left. So I should get one on the left and one on the right every time I do this. So now I need a chart. And I need numbers in between and on either sides of this to test f prime. Something smaller than -2, something between -2 and 0, something between 0 and 2, and something bigger than 2. And I plug those into f prime. Or I can plug those into the factors, give each one its own line. So if I plug into 4x, I get -12, -4, +4, and +12. 4 minus x squared. 4 minus -3. -3 squared is 9. 4 minus 9 is -5. -1 squared is 1. 4 minus 1 is +3. Again, 4 minus 1 is +3. And 4 minus 9 is -5. This changed twice in this row because we had an x squared here. And now I multiply down to get f prime. And Chase, this gives me the extremes. And Jordan, this tells me where we're going up and where we're going down. So it tells me about the behavior of f. Up, down, up, down. F is increasing here. Everything to the left of -2. It's also increasing here between 0 and 2. That's that union. It's the mathematical version of the word or. It is decreasing when x is in here or x is in there, -2 to 0, or everything to the right of 2. So my graph should look like a capital letter M. Up, down, up, down. Means I've got a local minimum and 2 local maximums. I need y values. I already know one of the y values. What y value do I already know? Aha! We did that up here. I need to plug in either -2 or 2. I only need to plug in one of them because symmetry. Same on the left as is on the right. So if I plug in the one on the right, I'll know the y value, and I get the y value on the left, the same number. If I put 2 back into my original equation, that is 8 times 4 minus 2 to the 4th, that's 32 minus 16, I get 16. That means this one is 16 also. I can add 2 more dots to my picture, right? Back up here, I could add dots up there. Yes, ma'am.
Because when I back it, I feel like I've gone to switch those points, so it's like on the test and stuff, it's best to show how it thought, like the this process.
Oh, yeah. Most often, I'm actually not even interested in the picture. I'm interested in getting all this information to use it. As a matter of fact, that's the lead in for what happens after. After break, when we come back, I'm going to do more problems like this, but those problems are focused around using this information to solve real life situations. It's nice to be able to draw pictures. Woo. But if I graphed this equation just to start with, if I just graphed 8x squared minus x to the 4th on my standard window, I do have a problem. The graph's cut off, isn't it? So this is where I start to go, well, where is the top? Is there anything else going on in this picture that I missed that's down below? Because I clearly have more stuff happening. How do I know there isn't more interesting stuff down here or up there? That's what this tells me. But now I can actually say, oh, I really only need to go as high as 16, right? Let's go a little bit higher so we can be sure we see the actual top. Oop, wrong number. I don't want to change that one. I want to change the y value. I can type 2. And now I actually see more of the stuff, right? From f prime, I get most of the information about my window. I know there's nothing else going on outside this picture because all the graph does is come up from this side. And all the graph does on this side is go down. So that's all that's cut off in this picture, is the fact that it just keeps going down and down and down on both sides. So in terms of the picture, this is almost all of the interesting stuff. There's only 2 other points I want to look at. Because clearly, my convexity, my concavity, changed here somewhere. I'm concave down here. I'm concave down here. I'm concave up here. What happened? Where did that switch occur? That's what I learned from F double prime. So the one other thing I would do is check for inflection points. And if I'm going to change concavity from positive to negative or negative to positive, I'm going to go through 0. So again, I need to know where that's 0. Or doesn't exist, but this is a polynomial that exists everywhere. I can simplify that fraction. 16 over 12 is 4/3. So I take the square root. I get the square root of 4/3. I have absolutely no idea on the face of the planet what the square root of 4/3 is. But I know it's a little bit bigger than 1. Because 4/3 is bigger than 1. So I know that number is between 0 and 1. So 0 can be here and 2 can be there. And that means -2 can be over here. And these can be my test numbers for f double prime. Take -2 and plug it into f double prime. 16 minus 12 times -2 squared. -2 squared is 4. That's 16 minus 48. That's negative. All I care is that it's negative. That means we're concave down here. If I put in 0, I get 16 minus 0. That's positive. My second root is positive. We're concave up. Put in 2, symmetry, and concave down again. Chase, this also reaffirms where my maximums and minimums are, right? -2, 0, and 2, those were my critical numbers. I have a horizontal tangent line. If I have a horizontal tangent line, I'm concave down, I must be at the top. If I have a horizontal tangent line and I'm concave up, I must be at the bottom. Maximum, minimum, maximum. I am concave down on -infinity to -√4/3 or √4/3 to infinity. I am concave up on -√4/3 to √4/3. And that means I have inflection points. That means I have to plug in those numbers. I am the first person to tell you plugging in those numbers sucks. But if I go back and I look at my original equation, I'm squaring that number. That gets rid of my square root, right? So if I put in 4/3, I get 8 square root cancels by the square minus, then I'm going to square it again, 4/3 squared. So that's 32/3 minus 16/9. Ew. Wait a minute. This is 96/9 multiplied by 3 on top and bottom minus 16/9. That makes this 80/9. And it makes this the same thing because of the symmetry involved. And if I take a look on my calculator and I put the trace button and I type in the square root of 4/3, 80 divided by 9 is 8.8888888. It worked. I might actually adjust this picture because I really don't care about anything bigger than, say, -4 on the left and 4 on the right. So I could adjust this picture to see that a little more slowly. I can even see where the curve changes a little more clearly here, can't I? I can see it flattens out as it comes from one side down to the other. There's that little straight bit right in past 1. Again, the first time I learned to do this, this was the only graphing device I had. So that's the reason I get to this point and I'm like, oh, now I can draw this by hand. I have the technology. I don't need to make the drawing by hand. Incredibly accurate graphs were drawn this way as far back as the 1800s. At that point, we started to develop technology to draw better graphs. There's a lovely exhibit in the National Air and Space Museum of a graphing device that is clockwork. It's made out of gears. It is roughly the size of the floor of this room stood on end. That makes it about 3 stories tall. You turn a crank and it draws a graph. And as you put in different gears, it adjusts the behavior of that. Devices to do this were invented as far back as 2,000, 3,000 years ago. The Greeks invented a device called a trammel, which allows them to graph perfect ellipses. There are 6 or so examples in the textbook that walk through exactly the same set of steps we did. All of them for every problem. Please read them. Because this took us 30 minutes just to do this one. Doing all of this all together, that's a long pain in the neck. But I got lucky in the problem I just did. And I saw that there were no asymptotes involved. Here is a rational function. Does this have a horizontal asymptote? We had a rule about rational functions, about powers, or I could do L'Hopital's rule a bunch. Does this have an asymptote? A horizontal asymptote? Why not, Jack?
Because that's when the power is greater on the bottom.
Or,
Equal.
exactly. If we have the power on top being equal to the power on bottom, then we get something other than 0. If power on the bottom is bigger, we get 0. But in this case, power on top is bigger. So I should be going off to infinity as I go to the right. X raised to the third divided by the quantity x squared plus 1. Standard window. Now, wait a second. That graph really kind of looks like a straight line, doesn't it? There's that funky wiggle in the middle. But other than that, that looks like a line. This actually does have an asymptote. It's just that that asymptote isn't horizontal. I'm going to graph the line y equals x. Holy guacamole, look at what happens as we go off to the right. That curve is getting closer and closer and closer to that line, isn't it? You can barely tell them apart over here. Same thing's going on down here. This function has an asymptote, but the asymptote is not horizontal. What the? Jack, in this case, the reason that happens, because the power on top is exactly 1 bigger than the power on the bottom. I rigged this problem. If the power on top is exactly 1 larger than the power on the bottom, I do get an asymptote. But it's not flat. It's tilted. This is called a slant asymptote or an oblique asymptote. Now the question, how did I know that the appropriate line would be y equals x? And the answer is division. That's what this over means, right? I'm dividing. Without your calculator, how would you do this? I know it was a long time ago that you learned how to do long division. Do you remember doing long division? You take 13 and go into 372. Remember that garbage? Gosh. How many 13s in 37? Two of them. 2 times 13 is 26. I subtract. Now I have to know how many 13s are in 112. Well, yeah. 13, 26, 52, 104. I just multiplied by 2 each time, right? 8 of them give me 104. If I tack on one more, I'll get too big. So there are 8 of them. 8 of them, 104. I have a quotient, I have a remainder. Yes? I can do that with these. Polynomial long division works the same way. If I divide x cubed by x squared, what do I get? Ignore the plus 1. X cubed divided by x squared. So I'll put that up there and I'll multiply. X times x squared gives me x cubed. X times plus 1 gives me plus x. I subtract. I get a negative x. That power is smaller than this power. That's my remainder. This number was smaller than this one. So if I think about the division I just did, I have x cubed divided by x squared plus 1 is x plus a remainder. Just like up here, I have 372 divided by 13 is 28 and 8 over 13. The remainder gets turned into a fraction. The remainder got turned into a fraction. This is why I know this is an asymptote. Because as x goes off to infinity, this is going to go to 0, isn't it? And that's going to leave me a straight line, y equals x. Son of a bitch. If the power on top is exactly 1 larger than the power on the bottom, you're going to get a diagonal asymptote, an oblique asymptote. And to find it, you do this division. Another example. 2x cubed plus x squared plus x plus 3 divided by x squared plus 2. Power on top is 3, the power on the bottom is 2. I'm going to get a line. What line? Whatever my quotient is up here. There's my remainder. After I do the division, quotient, remainder, that's the line that makes up my asymptote. If you graph this and you graph the line y equals 2x plus 1, you'll see that same sort of approach we saw here. Which means in the long run, this function behaves like a straight line. It's big O of x. Computational complexity will come into play if you're a computer science person. I hope you have a wonderful Easter. I will see you on Wednesday, which I believe is question and answer. Or is that my actual next piece? Yes. Wednesday is question and answer day. I will see you then.